So, hello, my name is Chiara Rossi, and today we'll present the early work of my PhD, which consists in investigating the working memory network dynamics in MS. So, multiple sclerosis is the most common chronic neuroinflammatory disease of the central nervous system presented in young adults. And if we look at the pathophysiology of the disease, this is characterized by inflammatory events within the central nervous system that lead to demyelination and axonal loss. Therefore, at the microscopic level, we see disruption of the neuronal circuits, and this is also reflected at the macroscopic level, where the whole brain structural networks are disconnected and disrupted. So we know that severe structural network damages do have severe implication on the functional networks, and this has a great interest when investigating the cognitive impairment in MS. So cognitive impairment is a growing research field actually in MS care, because cognitive impairment has a big impact in the patient's quality of life. However, it is extremely difficult to delineate cognitive impairment and actually describe the disease mechanisms underlying cognitive impairment because of the great inter-subject, or better, inter-patient variability of the disease manifestation. So recently, neuropsychologists have came up actually with this new description of cognitive impairment, utilizing cognitive phenotypes, so different profiles of cognitive impairment that appear throughout the MS population. And we see that within all the cognitive phenotypes, there is attention, memory, and executive functions that are the most affected domains. Today, I will focus in one specific executive function, which is working memory. Working memory is a function that allows us to acquire information, maintain it while manipulating it in our short-term memory, and then retrieve it as well. So to perform well working memory tasks, we need attentional control, we need decision-making, we need processing speed as well. So by tackling working memory, we can actually have broader overview of the cognitive status of a patient. There is great literature on that describe the neurophysiology of working memory, both in healthy subjects but also in MS. However, most of the time, research has targeted specific domains of the brain dynamics singularly. So for example, the time domain was investigated by event-related analysis. Separately, the spectral domain was investigated via oscillatory time frequency analysis, and yet mostly fMRI studies have observed what is the network configuration in working memory and how it is impaired in MS. So here is where our research fits in, actually, because we try to provide a comprehensive overview of the temporal, spectral, and spatial domains of the working memory dynamics. So in my presentation and in my work, I try to answer to two questions. The first one is, can we actually describe in a comprehensive, data-driven way the spatial, spectral, and temporal dynamics underlying working memory? And we did so applying a computational model, so an HMM, a type of HMM, to analyze MEG data. And then, of course, the second question is, how can we actually describe the alteration of these dynamic network analysis in working memory, which is led by the pathology of MS? As I mentioned, we use magnetoencephalographic data, which provide us with the best temporal resolution to assess cognitive functions in general. So we have millisecond temporal resolution. We used source reconstructed data that were parcel using a 42 regions atlas. Just something to mention on the data set. The data set includes healthy controls and people with MS. However, we split the MS population into two parts. The first one, so the 54 subjects were not treated with benzodiazepine, and the second part, 16 subjects, were actually treated with benzodiazepine. The reason of the split is because we know benzodiazepine has a strong effect, so it alters significantly the network dynamics, especially when we look at MEG or EEG data. The subjects performed during the MEG recordings a visual verbal nback task, which is a widely known and a widely famous working memory task. And it consists of a sequence of letters to which subjects have to press a button when the target appears. And the target changes throughout the three conditions of the task. In the 0 back, the target is the letter X. In the 1 back, in the 1 back and in the 2 back, the target is every letter identical to the nth letter before, so n equal 1 and 2 for the 2 conditions. So, as I mentioned, we conducted a dynamic functional network analysis by applying the time delay embedded hidden Markov model. The HMM describes our data, so the empirical data that we have, the MEG recordings, as resulting from the activation of underlying hidden states. And these states are actually assumed to be unique and spectrally defined patterns of activation of the brain, which reoccur throughout time. The great advantage of this methodology is that we can provide a detailed description of the temporal, spatial, and spectral dynamic of these states simultaneously. And once again, an additional advantage of the HMM is that it does not compromise with the temporal resolution of our data, so we can infer the temporal dynamics on a milliseconds time scale for the activation of these states. Now, I will go into detail of how we describe the temporal, spectral, and spatial profiles. So regarding the temporal dynamics, we started from the MEG data. We ran the HMM. So in this way, we inferred actually the state-wise time courses. And the time course of a state consists of the time point by time point probability of activation of the state. Then we actually used these state time courses to run an event-related analysis, and in this way, we extracted the activation profiles of every state from the stimulus onset, so related to the task information. And as you can see here, we observed that mostly just 3 to 4, but mostly 3 states actually capture the dynamics starting from the stimulus onset, meaning that their activation profiles are significantly modulated after the stimulus onset. Regarding the spectral and the spatial configurations instead, so we always start from the MEG data, and then we weight the MEG recordings by the state-wise temporal time courses. And in this way, we can actually highlight within the MEG recordings only those time windows in which the specific state of interest is activated, and hence, then we can extract the spectral information from those specific time window which are related to the specific state under investigation. The spectral analysis was conducted via multi-taper, and we extracted the power spectral density distribution over the brain, as well as the coherence measure as measure of connectivity. As you can see here, we have considered the broadband, the frequency in the broadband for now, and then to extract the frequency-specific activation, we conducted data-driven decomposition of the frequency band, of the frequency spectrum by non-negative matter factorization of the coherence matrices, and we extracted 4 different spectral modes, we call them, which are data-driven frequency modes, frequency bands, which we can actually associate to the conventional one, because the first one, you can see, is actually covering the low frequencies, and then the second one is covering basically the alpha activity, and the third one basically the beta. So the first result I'm showing is actually the exploratory analysis on the healthy controls. You can see on the top the event-related analysis, the event-related profiles in which 3 states are actually significantly modulating their activation. If we look at the spectral and spatial profile of these states, the first one is actually a theta prefrontal state, so low-frequency prefrontal activity that can be associated with stimulus encoding and attentional control during working memory. Then afterwards, we see a decrease, so a suppression of the alpha-occipital activity that can, again, be interpreted as letter processing or local storage. And then lastly, we see a very interesting M300 profile of activation of a state that captures frontoparietal connectivity in the beta band. The following question is, but now what happens to this state when MS occurs in the MS population? If we singularly see the first state is actually the theta prefrontal activity, and we see that its activation is significantly reduced in the MS population. Therefore, this means that there is a decreased attentional control in MS. And if we run a peak analysis correlating the peak of activation of this state with the neuropsychological scores of the California Verbal Learning Test, we see that there is a nice correlation, meaning that decrease in attention control leads to decrease in verbal learning throughout working memory tasks, and this can be related to the working memory performance then. If we then look at state 5, so the activation of the M300 frontoparietal network, we see that there is no big effect on the MS population, but people with benzodiazepine, treated with benzodiazepine, then show a significant amplification of the state's activation. This is actually something that we did expect because the state captures the beta activity, and we know that benzodiazepine is enhancing the GABA-A conductance, which is related to the inhibitory interneurons activity that plays a big role in the in originating the beta activity. Yeah. So to conclude a little bit, we performed a data-driven functional connectivity analysis of the working memory network dynamics, and we identify in a super short time window that is shorter than 1 second, 3 main states that capture the dynamics of these in healthy controls. Then what we see is that the model captured how MS, so the MS-specific alteration of one network, the theta prefrontal activity, but the model could also identify which state was specifically altered by the administration of the treatment, which is benzodiazepine. So we think that our work demonstrates that there is room for improvement in actually bringing comprehensive and data-driven analysis of the network description of cognitive impairment and in general cognitive functioning actually. However, now the big challenge is how do we bring these very fancy methods and this very fancy analysis to a more clinical application. All right, so I will finish here my talk. I thank you all for listening to me. I thank my whole group, Professor Van Schependom, and questions.
So we have one question in the app, a traditional one. How did you decide on the number of states?
Okay. So it's a question that I get all the time. So it's a bit of a trade-off. So from the literature, the first time that the model was applied, the work provided by Diego Vidore and Andrew Quinn, they tried different number of states. The rule of thumb is try different number of states and then see how do you think that the dynamic is better described. Now, when we have tasks data, it's relatively easy to see the exact number of states that actually better describe your dynamics because you know the time window of interest. And if you increase a lot the number of states, so for example, I went to 8, 10, 12, then we see that there are lots of states that capture very similar aspects. So for example, the temporal dynamics of the task-evoked activation of the states are very similar. The spatial configuration of some states are very similar. So the trade-off is let's try to find a good number of states because the higher, in theory, then the number of states explains the best the variance within your data, but at the same time, a relatively lower number that allows you to capture, allows to each state to capture distinct spectral information without too much overlapping between states. So it's a bit of a trade-off, and I think it depends on the analysis as well. But in our case, so we tried different things, and 6 was the best.
Thank you.
Thank you very much.